So we'll start with week 12 session. Today's session is on cascade tunnel and also on turbine blade cooling. Okay, so I'll just discuss some questions first. The first question here is, in cascade tunnel, choose the correct instrument for measurement of velocity direction. So as you must have seen in the video lectures, we have to measure basically two things in a cascade tunnel. One is the speed. So there is we are going to place a set of so what is a cascade tunnel? There is a huge tunnel in which you place a set of blades, right? And between these blades you send in some velocity, so it enters at some c1 speed and then comes out at some c2 speed, right? And then we have to measure what is the change in this velocity and also what are the directions of the flow, either in the inlet or at the outlet. So the question is, how do we measure the direction of the velocity? So as you must have seen, the method is to use a yaw meter. So a yaw meter has basically two pressure probes, and then you rotate the yaw meter at a certain frequency. So first you'll calibrate the yaw meter at some particular direction, and say at this horizontal direction you set the velocity, the frequency with which you are rotating the cylinder, so that the two pressure probes, they balance out the pressure between them, and that frequency you will calibrate as theta equal to 0. And then given any flow, you can then find out what is the needed frequency of rotation for the yaw meter to balance the pressure probes, and then you can compare it to the calibrated theta equal to 0, and then tell what is the direction of the velocity at that particular position. Okay, so the instrument that is used is a yaw meter over here. Okay, then the next question is, choose the appropriate reason for the turbine blade cooling. So first of all, why do we need to cool turbine blades? We know that in a turbojet engine, what happens is, first the air is compressed in the compressor, then it undergoes combustion along with fuel, which is injected in the combustion chamber. So now when combustion happens, it is going to raise the temperature of the fluid that is flowing through your turbojet engine, and this very high temperature fluid then goes and impinges onto the turbine blades, where the flow is going to basically expand, right? Now what is the turbine blade seeing? It is seeing very high pressure and high temperature flow onto the turbine blades, and turbine blades are also made of some or the other metal. They cannot withstand very high temperatures. So what limits the maximum temperature that you can reach in the combustion chamber is the material of the combustion chamber and the material of the turbine blades. How much temperature can they really withstand? So if we can do some turbine blade cooling, then that will basically improve the maximum temperature that you can achieve in your turbojet engine. That will also increase the efficiency, right? So what is the reason for turbine blade cooling? It is, we need to increase the maximum temperature of the turbine, and that will result in increasing the efficiency and power output of your engine. Okay, so the correct answer is option B. Okay, then the next question is, for turbine cascade, the difference between the air angle at the inlet and the blade angle at the inlet is which of the following? So if we go back to what is an air angle, right? An air angle is basically the angle between the absolute velocity and the axial direction, right? And what is a blade angle? So blade angle is the angle between, say you have a camber line, and then tangent to the camber line and the axial direction. So now the question is, what is the difference between these two angles referred to as? Okay, so if you've seen the video lectures, it has been derived over here that the difference between air angle and blade angle turns out to be the incidence angle. Okay, now what is the incidence angle? So incidence angle is basically defined as, so let me just draw an airfoil over here first. So you have this airfoil which is placed in the cascade tunnel, right? And the camber line is, say, like this. So this is your camber line, and let us draw some tangents to the camber line. So at this point the tangent goes like this, and at this point the tangent goes like this, right? Alright, and this is the vertical direction. So the angle between this tangent to the camber line and the axial direction, this is referred to as your blade angle. Because this is the angle which your blade is actually making with the vertical, right? So I'll call this alpha 2 dash, and this is alpha 1 dash, right? And now we can draw the air angles. So air angle, as we said, it is, so I'll draw this with another color, right? So air angle depends on what is the direction of flow, right? So if there is flow coming in this direction, for example, say this is C1, and then there is flow coming in coming out, but it's, say, coming out in this direction, this is C2, right? So this angle, this entire angle is alpha 2, and this entire angle is alpha 1, right? And alpha 1 and alpha 2 are called the air angles, sorry, and alpha 1 dash and alpha 2 dash are called the blade angles. So now if you see carefully, the question is, what is alpha 1 minus alpha 1 dash? So if you see that, the question is basically asking you what is the angle between this tangent to the camber line and the direction of the inlet velocity. So that is nothing but the incidence angle, right? So that is how the incidence angle is defined. Okay. So then the next question is, cooling of turbine blades results in what? So does it result in the reduction in the number of stages of a turbine? Yes, because see, if we allow for cooling of a turbine blade, then the efficiency of each stage increases. That means the pressure drop per stage can be much higher. So then the number of stages which are really needed, that decreases, and it also reduces the number of blades that you need in a row. Then it also results in a higher flow coefficient. So it is essentially all of the above. So the answer here is all of the above, right? Okay. Which of the following is not a component of the cascade tunnel? So as you must have seen in the lectures, cascade tunnel, first there is an inlet, right? Then there is a diffuser. There is a conical diffuser because you need to slow down the incoming flow. And so maybe I can just draw. So there is an inlet, okay, and then there is your conical diffuser, and then you have a settling chamber. And after the settling chamber, we have some honeycomb structures. And these honeycomb structures, they basically they ensure that the flow direction, if there is any rotating components in the flow, they'll be cancelled out, and only axial flow will be given out. And then after the settling chamber, there is something called a contraction section. So what does the contraction section do? It directs the flow into this test chamber, okay, and in the test chamber you finally put your cascade. Alright, so we have a settling chamber, we have a honeycomb chamber, we also have a contraction section, but we don't have anything like a conical nozzle. So the answer here for which of the following is not a component, the answer is conical nozzle. Okay, now for a turbine cascade, air angle is the ratio of, so yeah, air angle is basically what we defined earlier. It is the ratio, it is the angle between the inlet air and the axial direction, right? So if you see the options over here, yeah, it is the first one, that is axial direction and the absolute velocity vector of the flow. Okay, then question 7. For a turbine cascade, the stagger angle is defined as what? So what is a stagger angle defined as? So again, if we draw the blade, let us draw this blade here, and there is a camber line and there is a vertical direction, right? So this camber line and the vertical direction, they make a certain angle with each other, right? So if you draw tangent to this, we saw this was the blade angle, alpha 1 dash. So what is the stagger angle? Stagger angle is defined as the angle between the axial direction and the chord line. So how do we define the chord line? Chord line is anything which is joining the leading edge to the trailing edge, right? So this is my leading edge, this is my trailing edge. So if I draw a line joining these two, I just extend this, okay, and we have this vertical direction, right? So I'll redraw the vertical direction. This is the vertical direction. Yeah, so the angle between the vertical direction or the axial direction and this chord line, this is called the stagger angle. Okay, then so here it is this option D. Alright, then question number 8. For turbine cascade, the difference between the blade angle and the air angle at the outlet is what? So again, we have seen what is a blade angle and what is an air angle, but then at the inlet we saw that the difference between them was equal to the incidence angle. So now the question is, what is this difference signifying at the outlet? Okay, so at the outlet it is basically the deviation angle. Okay, so again we'll go back to the same diagram. In this diagram you can see that there is this alpha 2, which is your air angle, and alpha 2 dash, which is the blade angle, and the difference we are asking is what is alpha 2 minus alpha 2 dash. So which is essentially, so if I highlight this with another color, this it is this angle, right? So that is how much is your flow. So ideally you would expect the flow to come tangentially outside, tangential to the blade direction, but it doesn't come tangential, it deviates, and this is defined as your deviation angle, right? So the answer over here to question number 8 is deviation angle. Okay, so question 9. In a cascade tunnel, honeycomb structure and wire vessel is mainly used to, so like we said, we want to make the flow streamlined. So okay, second option is immediately right. It reduces the turbulence present in the flow. So all the vertical structures, it will just remove that, it will straighten it out, so it will streamline the flow, so it's no more turbulent. It will reduce the random motion of the flow. So answer over here is all of the above. Okay. Okay, I'm sorry. Let me just use a highlighter. Yeah, so the answer is all of the above. Which of the following is not a cascade variable? So what is a cascade variable? Anything which you use to study the dynamics of this set of airfoils inside a cascade tunnel, right? So it is important that you analyze the cascade cascade of these blades in a compressor or a turbine, and it depends on the geometry of the blade, right? So it depends on pitch chord ratio, it depends on it also depends on the flow variables, like what is the inlet flow and so on. So the only thing that is does not matter over here is the camber angle. Okay, so the camber angle is not a cascade variable. It defines the geometry of the airfoil, but the only thing that we actually use is the pitch chord ratio, because what matters to me is not the blade shape itself. So what does the camber line define? It defines how curved is my airfoil. But what does the pitch chord ratio define? It defines how far are the blade spaced. So if this is a blade, how far are they spaced, right? So that is the pitch, and what is their chord length? That is L, right? So this pitch chord ratio is important, and the flow is coming in at what velocity? So Reynolds number is important. At what direction is the flow coming in? So the incidence angle is important. How curved is the geometry of the blade? That is not a cascade variable. Okay. Okay, so then the last question is for a turbine cascade, the summation of the air angle at the inlet and the outlet is termed as what? So again, let us use this blade that I've drawn here, and this is the axial direction. Okay, and what is air angle? It is the angle made by the inlet air. Over here C1, and over here it will be the outlet air is going to be C2. It will make some angle, air angle alpha 2. This is air angle alpha 1. So let us just draw these vectors like this. So this is C1 and C2 is coming out like that, right? So now if I draw it with respect to the vertical, so this is alpha 1, right? And this is alpha 2. And they are asking you what is alpha 1 plus alpha 2. So clearly the flow was coming in like this, and the blade has turned it into that direction, right? So this is the deflection angle. So alpha 1 plus alpha 2 is nothing but the deflection angle. Okay. Okay, so I have one thing to discuss. We can discuss the pressure profile of blades in a compressor versus turbine. So we have seen that cascade tunnel is used to study these pressure profiles, but also we have seen in the earlier tutorials that actually compressor and turbine, they have different type of blades. So if you remember, a compressor, okay, so a compressor, it has blades which are not they're not very turned, right? So they are more streamlined, and okay, this is it should taper. So let me redraw it. Yeah, so this would be a typical blade in the compressor, but a typical blade in the turbine would be much more turned, right? The camber would be very high. Okay, so this is fine. So this is these are the typical blade profiles, and as you must have seen in the video lecture also, so there is something called a suction side, okay, suction side and the pressure side. So the top portion, this is the suction side, and here this is the pressure side. Why this is called the pressure side? Usually on the pressure side you'll see that the pressure is higher, and on the suction side the pressure is lower, which is why an airfoil geometry, it produces lift. Okay, so here also there is a suction side and there is a pressure side. Okay, so we should see how the pressure varies. Now if you remember again, in a compressor, what happens, in each stage there is some adverse pressure gradient, because we are trying to increase the pressure, we are compressing the air in a compressor. So in each stage, because the air gets compressed, then across this blade the pressure is going to increase, right? So across each blade I expect an adverse pressure gradient. Okay, adverse pressure gradient. But in a turbine, we expect a favorable pressure gradient. So if you were not to do any experiments, what you expect would be the pressure profiles. So naively one would say that okay, the pressure is supposed to increase, so you expect the pressure to increase slightly as you move across the airfoil, right? So if this is the direction in which you're moving, so let's say this is your coordinate system, you're moving in x direction, right? And you measure the pressure. So basically you put a lot of probes inside the airfoil and on the suction side and similarly on the pressure side, and see what is the pressure profile. So you would just say that because it's a compressor blade, you expect the pressure to simply increase, and in the case of a turbine you expect the pressure to simply decrease. But that's not how it is. So the airfoil geometry matters. So you can see that for example over here the flow is supposed to climb, right? In this much region it is supposed to climb, so it is going to have some different pressure profile. It is, and over here it is going to have a different pressure profile, right? So if you see the results from experiments in cascade tunnel, okay, so I'll draw the results over here. So let's see, this is on the y-axis. I will plot the pressure, and on the x-axis I will plot basically as we move along this airfoil, so x, right? And let me just copy paste this for the turbine as well. Okay, so let us first draw for what is called the pressure side. So as I said, on the pressure side there is usually a higher pressure as compared to suction side, and also we expect that the pressure is supposed to increase. But what happens is that pressure slightly decreases and then it increases and almost remains constant on the pressure side. So what I have drawn here is for the pressure side, and you can also draw something similar for the suction side. But in the suction side you see that the climb is much larger. Okay, so there the flow has to basically climb for a larger amount. So if the flow is coming in this direction, it has to go like this and like this, right? So the depression in pressure is going to be much larger. So it decreases much more and then increases much more. So on the suction side, after the maximum thickness position, the pressure will increase rapidly and the flow is going to see a very high adverse pressure gradient, right? So it is in this region where maximum amount of flow separation will happen. So this is the suction side. Okay, now if you similarly see the result for the suction side of turbine blade, it was expected anyways that it is a favorable pressure gradient. That means pressure should decrease, right? So the pressure actually decreases, and it decreases smoothly for a large range of x. Okay, and if you also see for the pressure side, the pressure side almost remains constant, actually almost constant, but in the end it decreases. So it decreases for some amount, but okay, you need to be a little careful. So it decreases, it remains almost constant and then it decreases. And if you compare this now again to the suction side, so this I am drawing again for the suction side, And as I said, for most of the region, like most of the length of the airfoil, we will see a favorable pressure gradient. But towards the end, there is a local adverse pressure gradient. So somewhere around this point over here, we start seeing an adverse pressure gradient. Okay, so this is a local adverse pressure gradient. And it is because of this local adverse pressure gradient on the suction side that we need to be careful about boundary layer separation in turbine blades also. So even though we said that turbine blades have favorable pressure gradient, and compared to compressor blades, they do not have the problem of boundary layer separation. Well, compared to compressors, the issue is much lesser in the turbine blades, but there is always some chance of boundary layer separation over here. So if the angle of attack of your turbine blades is very high, then boundary layer separation can be a very big issue in the turbines also, and there is loss in the total pressure, which is not favorable for our design. Okay, so yeah, that's all. Okay, thank you.